Okay, so today we're going to talk about the spectroscopy lab. Okay, so this can be found if you're under the lab content on the Canvas page. Spectroscopy lab information is located here. So this is a dry lab. Okay, this is very similar to the physical properties lab that we will do as well. So here, the purpose of this experiment is to identify the concentration of two cobalt solutions. So we know what it is. It is cobalt solutions, but we don't know what their concentration are. Okay, so here, this is entirely a dry lab. Almost everything is done for you. Okay, you're being given the raw data and the report. Okay, I am giving you the raw data, okay, and the report. All you have to do is write the conclusion. Okay, now that seems simple, and it really is, but let's take a look at what the lab is about, because there are some concepts within this experiment that we haven't quite gotten to yet. Okay, so let's take a quick look at the handout. Okay, so this is the lab report. Okay, this is what you're going to submit. I have given you the lab report. Okay, title, purpose, procedure, the data section, which is the Excel sheet as well. And then the only thing that I've left blank is the conclusion. So you just need to fill in the conclusion section. Okay, so let's look at what this lab is talking about. Okay, so some words in here that we haven't covered yet. Okay, things like this capital M. Okay, this capital M, in our physical properties lab, we did things in percentage. In this particular lab, we use a concentration called molarity. So concentration is how much stuff is dissolved in the solution. Okay, so the more stuff we put into our solution, the higher its concentration. Okay, think of it as if you're making Kool-Aid, okay, and you take one scoop of Kool-Aid and put it in your glass and stir it up, it might just be kind of colored water. If I take 2 and 3 and 4 scoops, it'll get sweeter and sweeter. Okay, so the super sweet Kool-Aid is what we would call a concentrated solution. Oftentimes stock solutions are purchased in high concentrations. So this would be something like a bottle of vodka. Okay, it is the highest concentration or a high concentration that you then dilute down. So that's usually what a stock solution is. Okay, so we're starting from a higher concentration and then we are making dilutions. Now we haven't talked about what dilutions are. It's not super critical for the understanding of this experiment, but we are taking a little bit and we're adding water to it to dilute it. Okay, again, you're taking that Kool-Aid and you're adding water to it to dilute it down. Okay, so that's what the procedure is doing. Okay, so what they're doing here is if we haven't done the physical properties lab yet, essentially in the physical properties lab, we are reporting density as a way to correlate to concentration, okay, to percent concentration. Because again, if you have a single glass of Kool-Aid and you put 1 scoop in there, the volume is not changing, right? The volume of water in your glass is not changing, but what's changing is how many scoops of Kool-Aid you keep putting in there. So as you keep putting scoops in there, the density is going to change because the mass is being changed. You're changing the mass by adding more Kool-Aid to it. And so if I take 1 scoop, that's going to increase it a little bit. Another scoop is going to increase it another more. And so in our physical properties lab, density is related to its concentration in percentage. In this one, that same glass of Kool-Aid, it may be very light to begin with, but as you keep adding Kool-Aid to it, it gets darker and darker. Okay, so what we use in this lab is called absorption spectroscopy. So we pass a light through the sample. As the sample absorbs light, okay, it measures how much light comes out the other side. And so we can correlate the amount of light absorbed by the sample to its concentration. Okay, so what we are reading is I'm going to put a concentration I know into the instrument. It's going to tell me what is it reading for the absorption. Okay, so it says I'm going to read this concentration at this value. And then I'm going to put a different one in there, and it's going to read this concentration at this value. And so you're measuring the machine's response to different concentrations. Okay, so that's essentially what they were doing. And so instead of density, we're using absorption absorbance as our value, okay? Just like in our physical property lab, we would create a calibration curve. So creating a calibration curve is a common standard practice for doing analytical analysis. If we want to know how much stuff there is, we need to create a calibration curve. How the instrument responds to various concentrations. Okay, so in this case, we have water as blank, right? So there would be no Kool-Aid in there. So it's what is the machine's response when there is no Kool-Aid? Okay, then I put a little bit, and then a little bit more, and a little bit more, and a little bit more. And so it responds, and it correlates these values into a nice linear trend. The absorbance goes up with concentration. Okay, as a result of this, the computer plots the best fit line of this data and gives us a y equals mx plus b. Okay, so if we haven't talked about it before, the r-squared value is a measure of how linear your data is. So the closer to 1 your r-squared value is, the more linear the data. Okay, so that means the better your calibration curve is. Okay. From this, we would plug our unknown. So we have our calibration curve. We would then measure our unknown in the same way. The unknown will give an absorbance value. So we would plug that absorbance value in for y and solve for x, and that would give us the concentration of our unknown. Okay. And so that's essentially what's been done here. So we created a calibration curve, same as we would have done for a physical properties lab. This is very similar to how many other analytical experiments are run. Okay, it's just a matter of what instrument you're using. Okay, so if we're just doing it via one sample of density, that's one thing. But if you run a calibration curve, you can do probably hundreds of samples. Once you calibrate your instrument, then the instrument will just continue to measure each new sample against that curve. So it'll just say, okay, here's the absorbance, boom, here's the concentration. Absorbance, boom, concentration, absorbance, concentration. And it can sit there and keep kicking out the value unknown samples for hours. So once the computer knows what the range is, what it's supposed to be, and then you're going to plug in your concentration in there, it will then tell you your absorbance, it'll tell you what the concentration is. Okay. So we do this a little more manually because, again, this is only like 1 or 2 samples, but this one takes it a little bit step above where we did in the physical properties lab. So in the physical properties lab, we just did 1 sample. Okay. So this is now looking at many samples. Okay. So let's take a look at the data here. Okay, so this is an Excel sheet. Again, some features here are going to be a little bit new. Now there's not really a whole lot on here, okay, that you specifically have to focus on, okay? I'm just going to talk about some of the terms here, okay? So the stock solution was 0.42 molar. Okay, so that is molarity. The capital M is the concentration. Okay, so anytime you see a capital M, you're talking about the concentration of the sample. Okay, so the first part in section A is just looking at the diluted volumes. Okay, how much volume did they use to make a dilution? Okay, or what is the total volume of the stock solution that they use to get the solution? So you can see that sample A, they use 3 milliliters, sample B, they use 7, and sample C, they use 12. So this you would expect that the concentrations are going to be going up because we're using more of the stock solution for each one. Okay, here is the absorbance value for each sample. Now what you'll see here is unknown number. So each row here corresponds to a single student. Okay, so this is student number 1. Okay, student number 2. So student number 2 had the same unknown number as student number 1. Student number 3 had unknown number 2. Student number 4 had the same unknown number 1 as students 1 and 2. So you have many samples being taken. So usually we will do, if we are concerned about statistically viable samples, we want to take as many samples as we can. That way we get better results. Okay, so here you now have replicate data of unknown number 1 and many replicates of unknown number 2. So this would give you a good representation of what is the concentration for number 1 and what is the concentration for number 2. rather than just doing a single sample. Okay, section B. So these are the concentrations for the calibration curve. So in the physical properties lab, we did 10%, 20%, 25%, 30%, 40%, 50%. Okay, here we are assigning actual concentration values to those. So the water is obviously 0. Okay, concentration of A, so this is a dilution value. So this is a calculation of this volume and the initial concentration. It's not really important to you. Okay, so this how they get this is not really important at this point. Okay, but the point is these are similar to those percentage values from the physical properties lab. Okay, so as we had percentages, now we have concentrations in molarity. Okay, so with each, in the physical properties lab, we would have measured the density of every sample. Okay, every sample in our calibration curve had a corresponding density. So here we now have the absorbance for every sample. Okay, so here is the absorbance of the water. There's nothing in there, so it's not absorbing anything. Solution A, there's a little bit. So solution A's concentration is 0.051. Okay, so it has a nominal response of 0.3. Solution B has a concentration of 0.11, so it's double A. And so it gives us an increased response because the concentration is going up. So it's, again, the solution is more colored, so it's absorbing more of the light passing through. Solution C has a concentration of 0.2, so double this, and then it has, likewise, an increased absorption of the light coming in. And then the stock solution, again, is double, and so we get, likewise, an increasing amount of absorbance. Okay, so again, these sections are not really important. Okay, you don't need to do anything with section A, you don't need to do anything with section B, and you really don't need to do anything with section C. Okay, these are simply just setting up the calibration curves. Okay, now, because you have many pieces of data, okay, so in the physical properties lab, you had one set of data. So it was easy to do a graph of just your data. Okay, but when you were running 100 samples, or in this case, 20 samples, you're probably not, you're not going to make 20 graphs. Okay, so a computer would not make a graph of every sample. Okay, it would simply keep the numerical values from the graph. We did a graph in the physical properties lab as part of our data section. We have a sample graph. Okay, we know what the graph looks like. Okay, but this is one data set. Okay, so we don't do this for every data set. So instead, we record the slope, the intercept, the r-squared value. Okay, so these are the values that the graph would give us. Okay, the slope, the intercept, the r-squared value. Okay, and the y value here, so the absorbance of the unknown is the same as it is up here. Okay, this is the same raw data. I just moved it down, so the data from above just moves down to the data in the bottom. So this is the same unknown and the same order. All of this stuff is in the same order. Okay, so here is the absorbance of the unknown. So just like in the physical properties lab, we would plug our unknowns value in for y. Okay, so here, this is our y value. We are plugging our unknown absorbance in for y. And so the resulting value then is x. We need to know what x is. X is the concentration of our unknown. Okay, this is the purpose of the experiment. What is the concentration of the unknown? Okay, now the only bit of data calculation you need to do is that if you were going to tell me what is the concentration of the unknown, what value are you going to do? You have 10 samples of number 1. You have 10 samples of number 2. Are you just going to pick one and say, oh, unknown number 1 is 0.051 because that's this first one? Okay, or is it 0.102? Or is it 0.045? Okay, or 0.065? Like which one are you going to pick? If you have a set of data, you wouldn't simply arbitrarily pick one as the concentration. The best way to handle a data set would be to do an average. Okay, so your challenge here, though, is that you need to get an average of the number ones and you need to get an average of the number twos. Okay, so how you go about doing that, you need to do, that's where the data processing comes in. Okay, this is where you have to do a little bit with this, okay, because you need to gather the number twos, okay, all the number twos, and what is the average of all the number twos? What is the average of all the number ones? Okay, because when you are reporting, I give you one sample. I want to know what is its concentration. Okay, so unknown number one, its concentration is X. Unknown number two's concentration is Y. Okay. Well, I shouldn't say X and Y because X and Y are right here. So I would say unknown number one's concentration is A, unknown sample number two's concentration is B. Okay, so they have individual values that you're going to report. It shouldn't be unknown number one is between 0.045 and 0.102. Okay, it shouldn't be a range. Okay, it shouldn't be a range. It shouldn't be around something. It shouldn't be about anything. Okay, we are using an analytical technique. This gives us numerical values. We should be able to do mathematical calculations and statistics in order to come up with a single value. What is it supposed to be? Okay, we'll talk about error analysis and things like that we'll include later. But for now, I want a single value. What is that value? Okay. So these concentrations here, you need to gather these together. So maybe group the ones and group the twos. Okay, what is the value? There is a right answer to this. Okay, there is a right and wrong answer because everybody in the class has the same data. I have the same data. So when I do my data, your data should match my number. Okay, so if you say unknown number one is 0.151 and that's not what I got, then you would be wrong. Okay, so again, you're trying to get as close to the real number as possible. Okay, so I want to know what is the concentration of unknown number one and what is the concentration of unknown number two. Okay, so and then now you just need to write the conclusion. Okay, paragraph, same kind of context as before. What was the purpose of the experiment? How do we go about doing it? What is the result? Okay, there is no further analysis part. The fact that there's one of them is 0.015 or something like that, it has no further meaning than that. These are just that's just a concentration. Okay, so what was the purpose? How did we go about it? What was the result? Okay, those are the three things you should be thinking about for your conclusion. Okay, but you need to get there with the numerical value. Okay, you don't really need the chart. The chart is there for your viewing. Okay, it's there to be included with the lab report with the document that's already in the document. Okay, so this is just a dry lab. You're writing the conclusion. We are focusing on our conclusion writing as I've taken everything else taken all the other bricks out of the cart. Okay, so focus. What are the two values? Okay, that's it for this lab.